Welcome to Universe Boundary in Einstein 1931, same as Lemaitre 1927. We're talking about our universe, the various cosmological models, theories attempting to explain it, and in particular, depending on which models, the various boundaries or limitations that apply, and interestingly, in our modern astronomical history, since general relativity. All the models of consequence can be traced directly to either Albert Einstein or Abbé Georges Lemaitre. They are arguably the two greatest cosmologists that we have in our modern astronomical history. And the models we speak of began, of course, with the first, the static universe by Einstein in 1917, shown on the left, followed pretty quickly by the expanding universe, that through the iterations you see there, including Lemaitre's, has gone on to become the standard cosmological model we have today, the Big Bang theory shown in the middle. And on the right, this dynamic equilibrium universe by Lemaitre in 1927, an alternate model I spoke a bit about last year of interest because it incorporates both the models you see on the left. You have the static universe in the center surrounded by the expanding universe and all that contained within the confines of a black hole defined by the Schwarzschild radius. And these models aren't as different from one another or nearly as hard to understand as you might think when we do the math on the various sizes involved. You can see that they're all based on variants of the Schwarzschild radius. The Schwarzschild radius of the event horizon of a black hole, probably the best known equation in all of physics other than E equals mc squared. And as said, whether the models are based on the Schwarzschild radius shown at the top, or the Hubble expansion radius in the middle, or the Einstein static radius on the bottom. Same architecture, just GM over C squared, and differing from one another simply by the factors shown circled in red there, and all they involve are factors of either 2 or factors of pi, and pi probably meaningful in terms of our universe having had some spin, some orbital angular momentum, as well as the radial velocities you hear about in the standard model. But having done the math, you can see that we are comparing these models in very accurate terms. You're looking at them in exact scale to one another, so you can see that the Schwarzschild radius is in fact exactly double the size of the Hubble expansion radius. It's exactly pi times the size of the Einstein static radius. But just dispensing with the math, rigmarole, really the point of the model on the right, beyond the fact that it incorporates all of the models of general relativity possible. I mean all of the changing, the dynamic, expanding models, all of the unchanging, the static, stationary models into one super hybrid. Its use for us today is the fact that just by adding to this one expansion sphere that we have today, the other two spheres that you see there, this outer and inner boundary, just by adding boundaries to the expansion radii possible, you solve two big problems with the current model, the nothing before, the nothing beyond. So problem one, nothing beyond. The idea that our own individual universe contains all the space and time in existence. I mean, come on, our universe is visibly, demonstrably finite. Much more palatable. You define an outer boundary, the universe goes this far and no further, and therefore thereafter space and time can continue infinitely beyond that, as they logically must. But the bigger problem too, this idea that everything in existence exploded into existence out of absolutely nothing, I mean, come on. It's just a violation of all the central tenets we hold dear as scientists. Conservation laws don't start. Much more palatable than the idea of a single one-shot only Big Bang emerging out of nothing and going on to who knows where, including infinity, is the idea and the probable fact, honestly, that since our universe has a minimum finite size defined by Lemaitre's model, we're just talking about innumerable Big Bangs followed by innumerable big crunches, and the universe continuing eternally in a cyclical, dynamical, stationary fashion. And a picture that you could see fitting in like this. Our universe is just one amongst an infinite number of universes. And I thought that was pretty brilliant, but not so fast. I think other scientists require more evidence before jumping on the Lemaitre 1927A model bandwagon. And I was looking at the model with you again here this year because it's been a very good year for providing not only more, but in fact abundant new observational evidence. I mean, on the theoretical front, it's as though in the last year, Albert Einstein, the father of general relativity himself, rose from the grave, so to speak, by publishing a theory that he never did publish in his own lifetime, but that provides a dynamic equilibrium universe that in its basics is quintessentially identical to Lemaitre's model, and I'll show more in a minute. But we know about this theory thanks to, in part, Harry Nussbaumer, who not long after discovering it emailed me this, and he was surely right, because when I learned that Harry and Cormac O'Rafferty, working independently, had discovered this long-lost theory of Albert Einstein, so important it was covered in Nature News. I was just amazed. I mean, you can see the handwritten manuscript by Einstein. You can see the fact that it is on the cosmological problem. It is by Albert Einstein. It does include an elegant mathematical equation describing the model that we highlight here. And you can see for yourself, reads, without time to go into the terms, just it does read alpha squared equals, minus this crossed out part, alpha squared equals kappa c squared rho over 3. It's the same equation you see reproduced here, alpha squared equals kappa c squared rho over 3. And that through this intermediate steps, it happens to reduce to exactly the same equation that Lemaitre's dynamic equilibrium theory is based on, as shown in my paper describing Lemaitre's model, published in the Journal of the Royal Astronomical Society of Canada, 2013. Same as published by Lemaitre in his doctoral thesis, submitted in 1925, earned at the Massachusetts Institute of Technology in 1927. And none of this, ladies and gentlemen, to be confused with what Lemaitre is famous for from 1927. This is a paper published in French, deriving the very first ever Hubble constant of expansion published for our universe. That is Lemaitre's contribution to the simple Big Bang that we have. We are talking about his alternate model on the right. We're talking about the model that allows this elegant, this grand simplification where all of the universe's basic properties, from her age, size, mass, it can all be deduced as simply and easily as using combinations, just the two most fundamental constants we have in physics, c and g. Take the top, the size, the radius, just equals c squared over g. Never mind the dimensional fudging, it just amounts to 1. Anybody here with a calculator, that calculator, and God is my witness, plug in c squared over g and out comes this number of centimeters that does equal that number of light years, and that is how we arrive at this comparison. Now, there is a difference. In Lemaitre's dynamic equilibrium universe, all the vacuum energy is contained within this otherwise hollow vacuum energy-filled inner sphere here, Einstein's old static universe. In Einstein's dynamic equilibrium universe on the right, the vacuum energy is contained throughout the space, and what it's doing, theoretically, is creating new matter in exact proportion counterbalance to the old matter that's escaping beyond that outer boundary due to the expansion of the universe. But of course, we appreciate today that matter escaping beyond that outer boundary is impossible, and Einstein pretty quickly abandoned this theory. Our point in showing it to you, though, and the discovery of its existence in just the last year, is that it lends a lot of gravitas, a la Einstein's name, honestly, and theoretical support, chutzpah, really, because the equations are basically the same, the outer boundary is basically the same, to our idea that Lemaitre's model, shown on the left, could prove not only interesting to our astronomical history, it could in fact prove important to our astronomical future. I say that mostly, though, because of the overwhelming observational evidence that's accrued in just the last year or two supporting Lemaitre's model, and this goes beyond the 14.2 billion year age predicted for our universe by Lemaitre's model compared to the 13.8 billion year age you hear about based on latest observations. That coincidence to within a couple of percent, it's just the tip of the iceberg. I mean, Lemaitre model predicts, for example, the matter density of our universe, just 1 over pi, saying it ought to be 0.318, intriguingly close to the default value that you see physicists use today, but identically close, ladies and gentlemen. That's our point. The most accurate single measurement of the matter density available to date. That's thanks to the European Space Agency's Planck mission in just last year. I mentioned last year the Hubble constant, predicted by Lemaitre's model 68.7. I didn't include identical to within the margins of error to within 1% of the same Hubble constant arrived at by Chen et al., Calabresi et al., who got that by studying all of the Hubble constants that have been published up to the years that you see. Same Hubble constant, again, to within the margins of error to within 1%, as the most accurate single measurement to date, available thanks to NASA's WMAP mission in just the last couple of years. And the real observational evidence supporting Lemaitre's model, and frankly, ladies and gentlemen, all but ruling out the simple Big Bang. It has to do with the fact that the Big Bang not only does have the nothing beyond, the nothing before problems, the real Achilles heel, the 500-pound gorilla in the room for the Big Bang theory, is the fact that it predicts a non-constant Hubble constant. See for yourself, the Friedmann-Lemaitre-Robertson-Walker model predicts evolution of Hubble parameter. It's saying that in the distant past of the beginning, our universe's expansion rate started out very quickly. So say it's c kilometers per second per megaparsec, and it's slowed to the 70 kilometers per second per megaparsec each day. So if you were to look back in time, say at a redshift of 1, you'd see double Hubble value, a redshift of 2, you see 4 times the Hubble value, and it looks like this on a linear scale. As you approach the limiting speed of light, shown on the right, 300,000 kilometers per second, Hubble constants shoot off the scale, even more dramatically in the fine scales that we measure Hubble constants in. And our point is, this is not supported by the data. When you look at the 7 Hubble constant indicators available over cosmological history, including up to as far as you can back in time based on the cosmic microwave background radiation, the Hubble constant has been a constant throughout cosmological history. This rules out the simple Big Bang and rules in either Lemaitre's model or something like Lemaitre's model with a Hubble constant. Something else this rules out, we've all heard of the vacuum energy. Its discovery in 1998, 1999, recognized by the Nobel Prize in 2011. It's not appreciated well that this vacuum energy was originally predicted in Einstein's static universe. It's necessarily part of Lemaitre's dynamic equilibrium universe to keep it in balance. And yet, the discovery has been interpreted as meaning ipso facto our universe's expansion rate is accelerating. I mean, come on. The observation that leads to this interpretation is based on, so look at the red data on the bottom there, the supernova. So you look at supernova, take them at an average redshift of 0.5, so 115,000 kilometers per second on this velocity scale you see here. And they are 0.25 mag fainter. They look about 10% further than they ought. So they reduce the Hubble constant at that point by about 10%, or say 7 out of the default value of 70, exactly where that cross is. But again, this is completely ruled out by the data. I mean, the dimming of the supernova can just easily be attributed to the fact that just in the same way starlight bends around the sun, it's probably true that light coming from supernova halfway across the universe are bent by the total matter of the universe. And that is a much more palatable explanation for the vacuum energy and the way it works. And accelerating expansion, I mean, deep in our hearts, we know this can't be right. Is exactly how Robert Kirshner described the idea of accelerating expansion. And he's one of the co-leaders of one of the 2 teams that discovered the vacuum energy in the first place. So we're talking about using our astronomical history, making use in particular of Lemaitre 1927A, to go about making new astronomical history, by which I mean, ladies and gentlemen, a literal revolution in cosmology. It's a revolution because this is going to bring us full circle back to the realization and awareness that there is, in fact, an old model of general relativity of consequence that at first might seem more complicated to live with than the simple model we have today shown in the middle. But I assure you, ladies and gentlemen, in the long run, this is going to prove a lot less complicated for us to live with, because it is the only model of general relativity that allows us to account for anything at all, as said, beyond our own universe. It's the only model that allows us to account for anything at all, as said, before the Big Bang. And it's the only model that allows us to account for the fact that, as you saw, the Hubble constants over cosmological history are indeed constant, exactly as originally theorized. So to conclude, it's just the fact of the new theoretical evidence that's emerged in last year thanks to Einstein's long-lost theory, but most especially due to the fact of the overwhelming observational evidence that's accrued, that we are compelled to assert, perhaps even conclude, that it is Lemaitre's model that you see on the right that is going to prove more important to our astronomical history in the long run than the simple model we have today shown in the middle. Thank you, ladies and gentlemen.